Assalamu alaikum wa rahmatullahi wa barakatuhu. In the previous video, we have seen the per unit system of measurements where we define the quantity per unit is equal to the actual value divided by its base value of the quantity. And we have defined certain base values P base, Q base or S base, and S base equal to V base and I into I base. And similarly Z base is equal to V base over I base, and similarly Y base is equal to I base over V base, and Z base is V base square over S base. So based on these base values we can find out the per unit quantity. So we have seen this example in which we have figured out how it was easy to find out the different analysis of the transformer or the power system involving more than one transformers with different transformation ratios. Today we will going to look into a very important topic of the transformer, which is known as the voltage regulation and its efficiency. So the real transformers normally have the impedances in series within them, and the output voltage of the transformer varies with the load even if the input voltage remains constant. So voltage regulation is then defined as the quantity that compares the output voltage of the transformer at no load with the output voltage at full load. So this is VR, or the voltage regulation. Normally it is measured in percentages because it's a unitless quantity. So it is defined as a secondary no load voltage, or the output side no load voltage minus secondary full load voltage, and divided by the V secondary full load voltage. So that is actually 100%. Or in terms of primary windings, primary voltage, we can write it as Vp over A minus V secondary full load divided by V secondary full load multiplied by 100 into that will make it into the percentage. So the good practice to have a small voltage regulation is important, so that we have fewer losses inside the transformer, because the good transformer will give us the a small voltage regulation. So for an ideal transformer, because we said that the ideal transformer is the lossless device, so therefore voltage regulation will be 0, because no load voltage and the full load voltage will be same. So when this will be the same, so it will be a 0. So it is not always a good idea to have a low voltage regulation, though sometimes high impedance and high voltage regulation transformers are deliberately used to reduce the fault currents in a circuit. So sometimes we can make our transformers with the high voltage regulations. So the voltage regulation of a transformer depends on the magnitude of these series impedances and on the phase angle of the current flowing through the transformer. The easiest way to determine the effect of the impedances and the current phase angles on the transformer voltage regulation is to examine a phasor diagram. So phasor diagram, I hope you have studied it in your basic engineering courses. So we will use this phasor diagram to look into the how these currents and voltages will behave. A sketch of the phasor voltages and currents in the transformer. In all the following phasor diagrams, the phasor voltage Vs is assumed to be at an angle of the 0 degree. We take this Vs as the reference and we draw all the currents and voltages according to Vs. By applying KVL to the equivalent circuit, primary voltage can be found out as Vp over A, because this is in parallel, so the voltage across it will be Vp over A, which is equal to Vs plus R equivalent Is plus Jx equivalent Is. So this will be a loop and we will have this equation KVL. So a transformer phasor diagram is just a visual representation of this equation. So now, because our power system can work on various power factors, it could be a lagging power factor, it could be a unity power factor, or it could be a leading power factor. So we assume this Vs as our reference voltage, and Is, obviously, if it is a lagging power factor, will lag by angle theta. Now Is is multiplied with the equivalent resistance, and that will be added to this Vs, and then Jx equivalent Is, because of the J, it is a plus 90 degree, so it will make a at the 90 degree angle from here. So we will add this Jx equivalent Is. So the resultant will be Vp over A. Resultant will be Vp over A. So in this case, we can see that Vp over A is greater than the secondary voltage, or Vs, the reference voltage. Similarly, for the unity power factor, Vs, we have taken this here up till here as a reference. Because it's a unity power factor, theta is 0. So Is is in phase with the voltage. And we will add this R equivalent times Is to this Vs. That will be added here. And Jx equivalent Is, obviously it's at 90 degree because of this J, and that will be added to here. And the resultant is Vp over A. And now for the leading power factor, we have taken this Vs as reference. Is is leading Vs by an angle theta. This is the magnitude of Is, and that will be added to this Vs as R equivalent times Is. Similarly, from here at 90 degree, we will add Jx equivalent Is. For J, it will be 90 degree, and X equivalent Is magnitude will be added here. And the resultant is Vp over A. So in all of these phasor diagrams, we can see that the behavior of the voltage is based on the power factor. So here in the lagging power factor, Vp over A is magnitude of Vp over A is higher than Vs. Again, for the unity power factor, it is higher than Vs, but it is approximately somehow lower than V for the lagging power factor. And for the leading power factor, Vp over A is smaller than the Vs. Similarly, the efficiency eta can be defined as P out over Pn into 100%. This is the basic relation we know for any system where we want to find out the efficiency. So P out or Pn here in this transformer can be defined as P out plus P loss. All the losses, that it could include copper losses, hysteresis losses, eddy current losses. So copper losses are in the series impedance. Hysteresis and eddy current losses are lumped together in RC. The output power is P out Vs cos theta s. So the efficiency is then Vs cos theta s divided by Vs cos theta s, which is P out, plus copper losses, this one, copper losses of the series impedances, and core losses, which are due to this resistance RC, and they are the summation of two losses, hysteresis losses and eddy current losses. And even if we have some stray losses, we can add them here. Stray losses or miscellaneous losses, that could be a friction losses, windage losses, etc. That can be added to this relation to find out the efficiency of the transformer. Because this is a transformer, so we will not have any windage losses or friction losses. So we can have some other stray losses if we can find out, so we can add them. So to understand this phenomena, let's look at this example. It says that a 15 kVA 2300 by 230 volt transformer is to be tested to determine its excitation branch components, its series impedances and its voltage regulation. So we have to determine all the components that we have seen previously and also its voltage regulation. The following test data have been taken from the transformer. So we have this open circuit test, which is on low voltage side, and short circuit test, which is on the high voltage side. So these parameters are given from the experimentation. Now what we have to do is find the equivalent circuit of this transformer referred to high voltage side. So we need to find the equivalent circuit of this transformer referred to the high voltage side. Then we have to find the equivalent circuit of this transformer referred to the low voltage side. Then we have to calculate the full load voltage regulation at 0.8 lagging power factor, unity power factor, and 0.8 leading power factor using the exact equation for Vp. Then we have to plot the voltage regulation as load is increased from no load to full load at power factors 0.8 lagging, 1 and 0.8 leading. So what's the efficiency of the transformer at full load with the power factor of 0.8 lagging? So that's quite simple. We have calculated parameters using open circuit test and short circuit test, and then we can find out the voltage regulation at different power factors. So the turns ratio are given as 2300 by 230, which is 10. Now the open circuit test, from here first we need to calculate this power factor angle theta C, OC. So all the values are given, so it is 84 degree. So excitation admittance is thus IOC over VOC with the angle of minus 84. Minus is, remember, because of this inductive load. So that can be converted to this 0.0009454 into these rectangular coordinates. Now comparing the equations, RC and XM can be calculated, and RC is 1050 ohm and XM is 110 ohm. Similarly, we can find out the parameters with this short circuit measurements, where theta SC is equal to cos inverse of PSC over VSC ISC. So putting these values, we will get 55.4 degree. And then VSC over ISC is this, and ZSC is then R equivalent is straightforward 4.45 and X equivalent is 6.45 ohm. Now we have to refer these voltages to primary side. The series elements referred to the primary side are X equivalent and R equivalent will be the same. The resulting simplified equivalent circuit referred to the primary side can be found by converting the excitation branch values to the primary side. So we need to multiply them with A square, and these values will be then 105 kilo ohm and that will be 11 kilo ohm. Similarly, if we want to transform these impedances to the secondary side or towards the lower secondary voltage secondary side, so what we will have to do is divide these R equivalent as J equivalent as by A square. So dividing by A square, 4.45 is divided by A square, A is 10, so 100, so it will be 0.044 ohm, and similarly it will be 0.0645 ohm. Now, so this is what we had. So the next part says that calculate the full load voltage regulation at 0.8 power factor, 1 unity power factor, and 0.8 leading power factor. So the full load current on the secondary side of this transformer is IS rated, which is equal to S rated over VS rated, 65.2 ampere. So Vp over A can be calculated as by using this relation. Vp over A is equal to Vs plus R equivalent Is plus Jx equivalent Is. So at power factor of 0.8 lagging, so cos inverse of 0.8 will be Is 65.2 minus sign will be because that is the inductive load. Therefore, and it's the lagging power factor, Vp over A by putting these values here will be 234.85 at an angle of 0.40 volt. Similarly, voltage regulation then can be found out by Vp over A minus Vs full load divided by Vs full load. So Vpa minus Vpa is calculated here, and we know this 230 volt is given as Vs full load, and that will be it's 2.1%. Similarly, at unity power factor, voltage regulation can be calculated by the same relation by putting these values. So that will be 1.28%. Similarly, at the 0.8 leading power factor, we have the same relation, and putting these values, remember that positive leading power factor, this angle will be a positive value. And then we will get Vp over A as 229.85 with angle of 1.27 volt. And here we can see that our voltage regulation is negative. Negative means that Vp over A is smaller than output voltage, which is the secondary voltage. Now here we can draw their phasor diagrams. This Vs is taken as the phasor diagram, phasor reference. Is is given with the angle of 36.9 degree on the negative side. That will be added here by multiplying it with R equivalent. Then X equivalent Is at 90 degree will be added to this vector, and the resultant will be Vp over A, which is 234.9 angle 0. Similarly, we can plot this for the unity power factor and the leading power factor. So here we can see visually now that Vp over A is 234.9, just looking at the magnitude. This is 232.9 and it is 229.8. So as the power factor from lagging to leading, this Vp over A, this voltage will be reduced. This voltage is reduced. Now the last part says that the efficiency, we need to find out the efficiency. So we can find out the copper losses, which is Is square R equivalent. Straightforward, we have this Is. And the core losses are given by Vp over A whole square by Rc. So just look at the figure, because this Vp over A is across that excitation branch. So that will be a straightforward here. So that will be a 52.5. So P out, we can find out VSIS cos theta. This is 12,000 watt. So the efficiency is then VSIS cos theta by copper losses plus core losses plus P input, VSIS cos theta, sorry, P out. So that will be a 98.03%. So the last part of this question, it says that That's we have calculated efficiency. And there is another part. It says that let's look at the question. It says that plot this voltage regulation as load is increased from no load to full load at power factors of 0.8, 0.1 unity power factor and zero point 0.8 power factor. So this can be easily done with some simulation software. But on here we can do is we can find out 3 to 4 values for at different values of load voltages, and then plot them, for all of these voltage, all of these power factors. So what we will get at the end is this one. So this is the load current, that's the different load currents. So there is no load current, so voltage regulation is 0 for all the power factors. As soon as the current is increased, we can see that for the unity power factor, uh, sorry, for this leading power factor, the voltage regulation goes into the negative side. And for the unity power factor, and this is for the lagging power factor. So we can see that with the if we have more and more inductive load in our power system, the voltage regulation becomes worse and worse. So if we can design a transformer with the impedances that are in series, with the lower quantities, with the lower number, means we can use the good conductors and other parameters and good ferromagnetic materials that has the high permeabilities. So we can have these losses fewer, and the voltage regulation can be improved. Obviously, it will cost. So I will end this video here. So I hope you have understood this voltage regulation, which is very important topic. And if you have any further questions from this video, feel free to ask. Assalamu alaikum wa rahmatullahi wa barakatuh.